Let's do this. Give it a few minutes to let people show up. All right. First, we're going to give it another few minutes before we get started to let some people kind of trickle in. Okay, it is 6:30, and we're going to get this started. Okay, so we are going to start this off. I'm going to take this bit by bit as we have gone through. So your final will cover everything from labs 7, 8, 9, and okay, I know some of my numbers are out of order, so we're just going to go with what I have here, because it just occurred to me that my labs are still out of order. So, okay, so the first thing we're going to start off with is one of the first things we discussed in the class and for this semester. And one of the first things we started off with was contour lines. So we had something where we did a topographic map, and you remember that you had to, in your lab manual, you had to look at a matrix of numbers, right, that was inside of a box, and what you had to do is you had to connect each one of those lines together. But how did we do that? Well, we had a few ways that we did it, starting off with establishing two rules. So let me write this up here. Contour lines. Okay, so for contour lines, we established two rules. And the first, right, is that contour lines can't cross. Cannot cross. All right. So this is, just like Ghostbusters, you can't cross the streams. If you have contour lines that cross one another, you have done something wrong. You have broken physics. Something is not right. Go back and recheck your map. And here in a minute, I'm going to do an example of a contour map on the board here, and I'm going to show you how I would like you to set one up and how I'd like you to do it on the final. So the second thing here, right, is lines of equal elevation must connect. Lines of equal elevation must connect. But if you remember from class, if you were there, you remember that this is the one that I put an asterisk next to, because there is an exception here, and we will get to that. But remember, lines lines of equal elevation must connect. And we do have a bit of a caveat here that we're going to go over when I actually show you the example. Okay, so again, when creating contour lines, your lines can't cross. Your lines can't cross. They can get real close. They can get real close. They can get close to the point that maybe some of them will be almost indistinguishable. You won't even be able to tell the difference in between, the distance in between. But they cannot cross. And then lines of equal elevation must connect. Always. All right, so here's what we're going to do. Here's what we're going to do, class. I'm going to set up a matrix for you. I'm going to set up a matrix of numbers, right? And what I'm going to do is we're going to have, let's do, all right, so on your test, you will see a matrix of numbers that will be given to you. It's a bit like this. It's a bit like this. All right, and then we're going to go. All right, and then. Okay, so here we have a matrix of numbers that I have come up with, okay? And this is a simplified version. It's a simplified version, okay? Your example on the test will be a little bit more complicated, but it will follow the same spirit here. And what you're going to do is you're going to choose either start at a high point or a low point. I generally start at the low point because sometimes the high points can be isolated somewhere on the map. So for the low point, okay, oh, and we also have to do the contour interval. Sorry, almost forgot to mention that. So the contour interval for this map, right, for this map right here, so is going to be 5 feet, right? So contour interval is the distance between contour lines. Okay, distance between contour lines. So for this map right here, okay, we are going to do 5 feet. 5 feet. So since our lowest number over here is a 47, let's take a 41. My handwriting is terrible. It's a 47, a 49, and a 48, right? What we're going to do is we know that we want them to be nice, even numbers. Okay, that's what we want. So if we have a map like this, anything below this would be 45, 40, 35, and so on. But what we're going to do here is we see that we have high 40s and then a 50. So remember, when you go to do one of these, plot points, always plot points. I'll show you what I mean. So remember, when we go to put our dots on here, we have to do something called interpolate. And to interpolate, you take an educated guess as to where that line would be. So we want the 50 line in between here, right? Well, we have to take an educated guess where 50 is. But I've already given you one value. So you plot a point on this 50, right in the middle. Right? Well, then you have 51 and 49, so we'll go somewhere in between there. 52 and 47, let's say somewhere closer to here. 53 and 47, so somewhere right in the middle. Okay. You have 54 over here, but you don't have to put another line. But maybe if you just, I don't know, want it to be neater, right? You can just put it right there. And then what you're going to do is now that you have your points plotted, right? See it? You can connect. So here, to here, here, to here, to here. And here's where I say the lines of equal elevation connecting. So let's say we had a 48 or somewhere in the 40s over on this side of the map. We very obviously could not connect a 48 over here with a 48 over here. That would take some serious geographical gymnastics, which we're not going to do here. So what you would do is you would just make sure that that had its own independent contour line. So, and what we're going to do is we're going to label this 50 feet. Okay. Well, now, next thing we need is 55, because remember the contour interval is 5 feet. So we need 5 more. So we're going to the 55. So 54 and 58, somewhere in the middle. closer to 54. 61 and 53. Well, obviously that's outside of what we want here because that isn't in the values between 60 and 55, because that's what we're putting together here, right? So say put that over here, 59 and 52, somewhere closer to the middle. 57 and 51, somewhere closer to 57. 56 and 50, it's going to be closer to 50. Okay? Again, points plotted and connected. It's fine. You guys can see that. It's fine. All right, so 50, 55 feet. Plot the points, label 1. Okay? All right. Well, next line, obviously 60. So again, look between other points to plot. So here is 60, 60, closer to the 59. Now we got a 61 that's just kind of hanging out over here, kind of encroaching on the 50s area, but our 60, like right in here, but then we see there's a 58 over here. So we have to put the line somewhere over here. All right. And again, as you see here, I am running them off the map. Don't be afraid to do that. These don't have to be a big circle of lines. You can run them off when you're taking your final. You can run them off the page. That's fine. So connect them again. Right. Keep in mind your 60 here, and then run it off the page. So 60 feet. So what you're noticing here, and here's something you want to keep an eye on when you're making your maps, is that everything between the lines, all the numbers between there fall in between 55 or 50, or if they are one of those values, it runs through that number. So every number in between the 55 and 50 is 55, 54, 53, 52, 51. Right? So 54, 53, 52, 51. All right? So on for everything from 60 to 55. So we have 59, 58, 57, 56. Right? But since we don't have a value for 60, we had to interpolate where it was. Let's keep going. Let's keep going. So here we have, we're going to need the 65 line. Something to note. Something to note. Keep an eye on what's going on over here because we don't have any values here between 65 and 70, which means we're going to have an empty line in here somewhere. So let's do 65. So one here, right? One here. One here. Let's put one down here for good measure. All right. Connect them. Run it off the page and label your 65. All right. Now here, we need a 70 line, but there are no values between 65 and 70, right? So what we have to do is we just need to, again, interpolate where that 70 line would go. So maybe something right here. And connect it. Even if no values exist, the line is still needed. The line is absolutely still needed to show that there is a change in elevation, right? That there is a constant change in elevation. And that is our 70 foot. Okay. Almost done. Almost done. So now we need our 75 because we have 70, and we do have a 75 value over here. So we'll just plant the dot right in the 75 and then 77, put it over here, somewhere in between these numbers, right? And again here, so we'll go closer to here. And watch out for this 81. That's going to be a different line altogether. So let's just put this like right down here. All right. And connect. 75. Okay. All right, with me so far. Okay. All right. We're almost done. We're almost done. So now we're doing 80. Now we're doing 80. So 75 and 83. All right. Now you see we also have this much higher value over here that will be a line all its own. You see that that is on an integer that is where a contour line would be. Right? So we don't want to put the line through the 85. Right? So let's just say the 80 will be right here. So big gap in number, right? But only a small gap in space. So be very careful where you put that. Right? And again, we're doing 80. We're doing 80, so it has to go on this side of the 81. Right? So let's connect them. Okay, label your line. Okay, so now we need 85. Now we need 85. But keep in mind that you have a number between 80 and 85 here, but 85 is also your next contour line, right? So your number is going to go here. And here's where, with some contour maps, you actually have a artistic license here. What are you going to do with this? Do you want to run a line farther down the map? You can do that. Do you want to do that? You can do that. As I'm not giving you any more values in this empty space right here or right here, so that's perfectly acceptable. Because the numbers between, let me label it, as long as the numbers are between 85 feet and 80, like the 81 and the 83 are, it is fine. That is okay. So this is what a contour line, a contour map will look like. And again, I advise you, plot the points. So I know that we practice this in 3 different classes. Each one of my sections, each one of you practice this in your class. And you want to be sure that you plot these points every single time. A lot of the mistakes I noticed were from people that were just trying to draw the line down the board. Plot the points. It will help you out so much. It is like the biggest pro tip I can give you for doing this assignment. Okay, so to review, right? You need to know that contour lines can't cross, and that lines of equal elevation must connect. They must connect. All right. And the contour interval, or the CI, right, is the distance between contour lines. This is what you need to know for this. Are there any questions on this before I continue? Before I continue on to the next assignment or the next lab? Any questions at all? What you got? I'm going to give it like a minute. If you guys have some questions, I'm going to get some gummy bears actually while I wait. Gummy bears. No? No questions? That's fine. I'm going to continue to eat gummy bears. All right. Okay. All right. So the next thing we're talking about. We need to go through the lab manual here. So in the last assignment, right? In the earthquake, and I think it was called the earthquake and bonus, I think. Yeah, in the earthquake bonus material lab, I asked you to do some things on scale. We're actually going to touch on that real fast before we get into some of the other stuff, because scale kind of ties into maps a little bit. And I know we touched this later in the semester, but we're going to hit on that just a little bit now. Okay, so let's discuss scale. So we talked about scale in our very last class. A lot of you that were there know that we went outside and I used the sidewalk to talk about scale, right? And we talked about the different types of scales. Okay, so we had the verbal scale, okay, which is just saying one measure to another. Right? It is stating that it is one measure to another. Okay? All right. And then we had, right, so the verbal, and then we had the graphic scale. And the graphic scale is like bar graphs. So stuff like this. Right? So you might have seen this. So let's see, 0 to 1 mile. It might have a dot in there, or you might have seen something like this, right? And it'll be like, maybe this is all 1 mile, but this is like a quarter mile. And this is an eighth mile. And this is 16th, right? You might have seen something like this before. It's a graphic scale. So verbal scale is the act of saying the act of one measure to another, and you do apply units to this. So one measure or unit, right? One measure or unit to another. Or a graphic scale, which shows you, and this is something you see on a lot of maps, where it'll have that bar scale at the bottom. And you'll be able to take like a ruler and put it up to the map and be able to measure yourself how far some of the distances are. Now, don't get me wrong, that's not very accurate. That's not always very accurate. But it does help give you an idea of the scale of an area or the scale of what you're looking at. Okay. But the last one is the one that we spent the most time talking about. And the last one is the one that you will see touched on the most in the final, and this is a representative fraction, the RF. Representative fraction. Okay, so the RF, the representative fraction, is, and I'm sure all of you have seen this, has seen something that's like 1 to 10,000. So 1 to 10,000 what? Those of you who were there, I asked you, 1 to 10,000 what? And I got some interesting answers. But those of you there who may have seen me, took off my shoe and I said, well, 1 shoe to 10,000 shoes, right? Or 1 banana to 1,000 bananas, or 1 gummy bear to 10,000 gummy bears. Like, that is the way this works. It is applying 1 unit of measurement is that many units in real space. 1 unit of measure on the map is that many units in real space, right? Okay. And the types of questions you will see on the test are simple math. Simple math, right? So I will tell you, let's see, let's actually turn to the assignment here. Are 6 inches on map are equal to an RF of 1 to 50,000. 1 to 50,000. Okay. So how do we figure out how far that distance is on the map? How far 6 inches is? Well, if you said that you would just multiply the 6 by 50,000, you'd be right. But let's actually take a step back and take this a little bit slower, a little bit more procedurally. And what I would do is, you know that basically that means 1 to 50,000 is 6 to something else. Right? So in class, I told you to treat this as you would multiplying fractions. So just cross multiply, right? So this would come out to 300,000, right? There you go. So you take these two numbers and the result, but your result, here's something important I need to be sure to mention. Your result cannot be 6 to something else, right? You must always have a 1. You must always have a 1. So it's still 1 to 50,000, but if you are telling me that, or you have to convert backwards from this, right? It must always be a 1. And that is all you'll have to know for scale. So I think I will ask you to give me 2 of the 3 different types of scales that we talked about in class. Okay. And then I will give you like 1 or 2 questions about how to convert scale. 1 or 2 questions on how to convert. Okay, any questions? I'm gonna step away and get some code bears again. See if there's gonna be any questions. Okay, I'll take them. No questions? Okay. Well, here's that. All right. So next, we're going to talk about storm hydrographs. Give me a second to clean up here. And clean this one too, because for the next 2, we're going to have to draw some pictures. And you guys are going to have to draw me some pictures too on the final. All right. And again, remember, your final is completely online. You will not show up to class next week. You will not show up to class. If you show up to class, I won't be there. I won't be there. I know it'll break your heart. Stay at home. Keep your phone. All right. Also, all right, so let's talk about storm hydrographs. Storm hydrographs. All right. Storm hydrograph. Okay. So in your lab manual, I think this is lab. Hang on. Wait. Okay, I take it back. We're not talking about storm hydrograph. I'm thinking of the wrong class. I see there's 3 of you watching and none of you noticed. Thank you. Okay, we're talking about relative dating. All right. Okay. So relative dating. So for a while there, I had you guys coming into class, and I had you doing analyses of which layers of rocks were older than the other, right? So. Relative dating. So. I wish I could edit this because I just had a brain fart again. And anyone who's watching has just watched me have a complete brain explosion of galaxy brain. It's the gummies. They make you forget. They do. Let's talk about storm hydrographs for real, students. Listen, sometimes your mind goes somewhere else. Okay. Sometimes it all blends together. Okay, storm hydrographs. We're really talking about this time. I haven't confused my sections, I promise. That would never happen. That would never happen. I would totally have all of my sections completely in order. I promise I didn't think you guys were historical geology for a minute. Okay, moving on. All right, so we're gonna talk about storm hydrographs. And we started it off talking about storm discharge and stream geometry. Well, this is one of the few sections in our lab where we gotta do just a little bit of math. And I know that's scary. I hate it too. There's a reason why I'm a geographer and not a mathematician, because I'm bad at math. But this one's not too bad. Q equals W D V. That means we're multiplying. That's it. That's what you got to know. It's cool. Let's move on. I'm just kidding. We're not going to do that. Okay. So what does this mean? What does this mean? Well, if I were in class, I'd make you tell me, but I'm going to tell you instead. So I know this is riveting stuff. All right. So the Q is the discharge, right? Q is discharge. Okay. And the W and the D and the V, right? You ready? Ready? Width. Okay. Width. Depth. D is depth. V is velociraptor. Just kidding. It's not. It's velocity. Velocity. So to calculate the discharge, you multiply the width times the depth times the velocity. So what does that mean when we talk about the discharge? Well, what we're trying to quantify, usually we talk about this in meters per second squared. So we're talking, or cube, sorry. So we're talking about cubic meters here. So it's meters per second cubed. So what does that mean? Well, that means that if at any given time in a body of water, remember we talked a little bit about Minecraft here, right? Where you can sometimes plot blocks and you can measure that block, right? So if you were to go into a stream at any given time, let's say after a rainstorm, and you could pull out a block of that stream, right? What would the discharge be? How wide is that stream? How many blocks does it take, right, across that stream? Depth, how many blocks deep is that stream? And how quickly would a block flow past you during that? Okay? That's what we're here to answer. That's what we're here to answer. So you will have some questions that will read like, and I'm taking this straight from the book. We're going to do these straight from the manual. So the discharge of a stream has a velocity of 4 meters a second. So we're going to set this up as we go. 4 meters a second. So 4. No, we're not doing the volume yet. 4 meters a second. Okay. A width of 20 feet. Oh, for the purposes of this lab, so I don't have to have you doing any conversions, it'll just all be in meters. Right? Sorry. It's with the 5 feet. I also can't read. Change that to meters for right now. A depth of 2. All right. Need to find the Q. So let me rewrite this equation for you. Discharge, Q, equals 2 times 5 times 4. All right, so you take that across, and you have Q that equals 40. Right? Remember, we're doing meters per second cubed here. So your discharge, right, at any given time during this is 40 meters per second cubed. But of course, it's never that easy. Now I have to complicate this a little bit. So what happens if I don't give you one of these, but I give you the discharge? So again, we're going to take one right out of the book. So it says a stream has a discharge of 48 meters per second cubed. We're going to put equal here because remember we're setting up an equation, right? And a velocity of 4 and a depth of 2. Depth of 2, but we don't know the W, right? Well, here's what we're going to do. We're going to do this as you would a normal equation. You're going to take the variables you know and multiply them together, right? So you have 8. So essentially this is 8W, right? And 48. Okay, well, we have to get the 8 away from there, so we'll divide both by 8. Okay, so we get a width of 6, right? 6 meters. I implore you, when you see a question like this, set the equation up. Do not multiply straight across, because I guarantee you there will be a question where I will give you the discharge, but I will not give you one of these numbers. Do not just see 3 numbers and multiply them. That will be wrong. Set the equation up every time. So the points on the test, on the final, are out of multiple points. So if you go through this and you were like 48 times 2 times 4, you'd be wrong. And if you showed me no work, that would be just a straight up 0 on the question. If you get it wrong, but you show me the work, I can at least give you partial credit. So be sure to always set up the equation. Be sure to set up the equation, because this at least tells me, even if you get it wrong, I see that you're attempting to do the, you're attempting to do what I've shown you. So you're showing me the concept, because remember, one of the main tenets of my class is we're concept over detail. We will get to the details later. It's the concepts I want you to understand first. So remember, discharge is Q is WdV. Discharge equals width times depth times velocity. Width, W, times depth, D, times velocity. Right? And your answers will be typically, if you're giving me the discharge, it'll be meters per second cubed, or if you're giving me another number, you'll give me the corresponding number. So if it's velocity, it'll be meters per second. Okay. Be sure to keep your eye on that. Be sure to keep your eye on that. So let's talk about the storm hydrographs. So we make a storm hydrograph, right? We are going to talk about, one of the things we're going to discuss as we get into this is talking about urban rainfall versus rural rainfall, right? So when we talked about that, we talked about this in the sense that if rain falls, if equal amounts of rain fall, let's say in Atlanta and here, right? At what point, which discharge will be higher? If we get equal amounts of rain here and in Atlanta. And the answer to that question, I'm going to tell you right now, is going to be Atlanta, because the ground cannot absorb. So when you have asphalt and concrete and roads, that does not absorb water. As places like around here in Jacksonville would, where we have lots of fields, lots of areas of trees, that's not something that we will be seeing. We won't see water just, rushing down the street unless, our water table is really high. As you would in Atlanta, where you get rain and it's going to be flooding into the storm drains. Okay. And the term for that is flashiness, or the flashiness. It'll ask you which stream is flashier, and that will be the one that has the higher discharge over a shorter amount of time, right? So when you say that we get a flash flood warning, so the week that we talked about this, I remember that we had almost 4 or 5 days of rain heading up to that class. And every time it rained, every single time it rained, we got a flash flood warning because the ground was so saturated that it couldn't hold any more water, so the water had nothing else to do but flow somewhere else. So when we would get rain, the discharge would be higher because it just has nowhere to go. Okay. Well, how do you chart this? Well, I asked many of you to create a chart for me, and I'm going to quickly just show you how this is done. So you'll have your chart, right? Your X and your Y axis, okay? And usually what you're going to do is your X axis will be your time. Your Y axis will be your discharge. I am going to give you one data set on the final for this. One single data set instead of the 2 that you saw in your lab. And what I'm going to want you to do is just show me that you have the ability to understand the difference between the discharge and the time. And I'm going to ask you some questions about I'm going to be like, hey, you know, at what time was the discharge at its highest? You know, did you see areas of flash flooding? I will ask you that too, like areas where you saw that that the flashiness went way up or something. Keep an eye on it. But that's what you're going to do. And, I mean, what I'm going to ask you to do, and I'll just show you, is just plot me points, right? So you'll plot the points on the graph, and I want you to connect them, right? So you'll give me, you know, on your lab, I asked you to do 2, and I asked you to do them in different colors. This one, you're fine. You only have 1 line, and I'm going to ask you details about that single line instead of comparing 2 things against one another. Okay. So that is it for the stream discharge lab. So here is what I expect your graph to kind of look like. I mean, it's not going to look like this line. These are just random arbitrary points I placed on here to prove a point. But I will want you to know this stuff right here. How to do this equation. There are very few things I ask you to outright memorize, especially formulas or other things like that. But this is something you need to know. Discharge equals width times depth times velocity. You need to know this. Okay. All right. That is all I have for that one. And give me a second. We're going to transition into earthquakes. All right, clean up the, all right, so earthquakes are the last thing we go talk about, and that is our longest lab. So, how about you guys? Good. I miss rocks. I miss talking about rocks. Talking about rocks was fun. There's not enough rocks in this section of the of class. All right. Okay. So now, this is the earthquake lab. That's right, they're all different because I think my earthquake lab is lab 11. But I think yours is something different. Mine's 11. But we're talking about earthquakes. 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 All right. Let's get into this. This is the longest section. The longest section of the final. You will see more questions about earthquakes than you will anything else because this is such a long lab. Also, you are going to be drawing me some pictures. Draw me some pictures. So I think during the final you'll have 3 pictures to draw. I don't know. There's going to be some pictures. Be prepared to draw me things. You know I like things that are very visual. Science is visual, so we're going to do that. Anyway, all right. So let's talk about how we measure earthquakes. Let's start off with that. How do we measure earthquakes? Well, we use something called a seismograph. A seismograph. Well, what's a seismograph? Well, okay, it measures the waves thrown off of an earthquake. Wave measurement. And you will see that it looks something like, you'll see that it'll be like, yeah, look at this. And then, oh no, things are terrible. And then they're not so terrible anymore. Okay, you'll see something like that, right? That's very crude, but you know, you get the point. Okay, but this by itself, the way we measure this has a name. It's called the Richter scale. Richter scale. But the Richter scale has a friend. Richter has a friend named Mercalli. So, the Mercalli scale. So how are these two different? How are these two different? This would be a test question. How are these two different? Well, the Richter scale, okay, the Richter scale is quantitative, okay? quantitative, right? And the Mercalli scale is qualitative. All right. We will get into what these mean. If you don't know what these mean, I will do my best to explain exactly how this applies. So the Richter scale is quantitative, and we assign this a number from 1 to 10. Right? Okay, and the scale is, and I ask you guys to remember this, because this will be another test question, the Richter scale is logarithmic. I am 90% certain I butchered the spelling on that. But the Richter scale is logarithmic. What does this mean? Well, let me show you what this means for us. So let's say 1, 2, 3. Okay. So let's say you have an earthquake. Measures 1 on the Richter scale. Oh, it's got a strength of 1. We're going to give it a value of 1. Right? But as it goes up in strength, a 2 is 10 times heavier, stronger. A 3 is 10 times stronger than that. A 4 is 10 times stronger than that, and so on. We actually put the dashes here. It just keeps going up and 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 up, right? Multiply by 10. So 10 times stronger, a 3 is 10 times, or a 4 is 10 times stronger than a 3. 5 is 10 times stronger than a 4, and so on. You have to know this because I'm going to ask you a question. That question is going to be, you have something on the Richter scale that measured a 4. Right? So a 4. Right? But then later on in the day, you had one that was an 8. I will ask you, how much stronger is that 8 than that 4? I'm going to show you how to do this. I'm going to show you the real quick way to do this. So when you see this, I would write this down on your test, right? When I took this class, I did this. It was a few years ago, but I did this, right? So you'll give that 4 a value of 1, okay? But you know you have to go to 8. So you know the 5 is 10 times stronger than the 4. 10 times stronger than that, and 10 times stronger than that. So by using the logarithmic scale, you're going from a 4, and then you know that the 8 is 10,000 times stronger than the 4. 10,000 times stronger than the 4. Okay? Inversely, you can divide the numbers. You could divide the numbers, but again, you know, this is a good way to do it and less math and not as much room for error. I will ask you to do this. I'm pretty sure I'm going to ask you to do this twice. I think what I'll probably do is be like, how much stronger is a 3 or a 7 than a 3? And then I might ask you how much weaker is a 2 than an 8? And that way you just do the opposite. Do the opposite of this. Okay. So let's talk about the Mercalli scale. So we have the quantitative Richter scale, which means that we can assign it an exact number. We can measure it quantitatively. Okay. But the Mercalli scale is a little bit different. The Mercalli scale is a little bit closer to a scale that we know a lot about here in Alabama called the enhanced Fujita scale. The enhanced Fujita scale, not Vegeta, Fujita. All right. So the enhanced Fujita scale is a qualitative measure of earthquakes. We qualitatively measure the damage. And that's what we do. And this is something that, much like the tornadoes down here, sometimes we don't actually assign them a number for the EF rating until a few days after, so we have time to assess the damage and get a chance to measure maybe how far something was thrown or at what speed something impacted something else. And all of these things are taken into account. The Mercalli scale is much the same way. It's a qualitative measurement. Okay. Very much on that one. It's qualitative measurement that we can't really use a lot of. So when an earthquake happens, it tends to happen underground, right? But that's not usually how we assign it a location. Typically, we say the epicenter. The epicenter is above the focus. The epicenter is above the focus, and the focus is where the earthquake happens underground. Right? The epicenter is where it happens on the surface. It gives us a location. So let's say an earthquake happened in the middle of the desert in Arizona, right? Or New Mexico or something like that. We could say, well, it was 100 miles outside of Albuquerque. And that is the location we would give it on a map. But the earthquake actually happened underground, right? This is the same kind of logic that applies to when we talked about lava versus magma, where magma is molten rock that exists underground, where once it's extruded, we have lava, right? This is a bit the same. An earthquake happens underground, and it originates from its focus, right? But the epicenter is that point on the surface that we measure it from. All right, so let's talk about waves. So we're going to talk about waves. So when an earthquake happens, it throws off a lot of waves. And the two that we are concerning ourselves with in this class are the P waves, okay, and the S waves. So the P waves are able to travel through water and rock. So solids and water travel, right? They're solids and water, and they're faster. They're faster. S waves cannot travel through water, only through solids, and are slower. Now, one of the questions I had for the class when we talked about this was I asked you which one of these was stronger. Which one of these did the most damage? So when we look at that, we want to look at the wavelength. So P waves have a very high wavelength, right? So they're very compact. So they tend to, we talk about high wavelengths, we're looking at something like this. So if any of you are in photography and you're familiar with the UV spectrum, this is, when you have very high wavelength objects that are very close together, right? But the waves are very close together, but S waves have a nice flowing pattern. And here is the problem. This tends to be the struggle here. So what happens is these tend to move faster. They just hurry their way through, right? So for an example, I showed you that Richter scale. I showed you that. So let's say here is, okay, this is leading edge, right? I'm going to do this in different colors because P waves are in blue and S waves are in red. And the S waves arrive. And you get these crazy, but you see that there's a difference. There's a difference here. And then it goes back to the P waves. And the S waves, so these are measuring the amplitude. And this right here are your S waves. Okay. All right. So we can measure these by seeing how much time it takes for the S waves to arrive. Generally, we get the P waves first because they move faster, and then we get the S waves. And we can see, chart their speed, and maybe talk to other seismograph stations to try and figure out, triangulating it or figure out where it started. Okay. All right. So I'm not going to ask you to triangulate. Because it's not something that I don't think can easily be done on a test. But I am going to ask you to know these. You're going to have to know some details of the P waves and the S waves. This is a very long lab. The earthquake one, I definitely advise you to read. the earthquake lab. All right. Okay. That is it, I believe. Do you have any questions? I'm going to leave this open for like another 2 minutes to see if there's any questions. Just going to eat more gummy bears. I'm sitting here and wait for questions. Okay. All right. If there are no questions, I'm going to end the stream here. Good luck on your final. Final starts on Tuesday. Yeah. It will be open until Thursday. You must take it. If you don't take it, I can't help you. So please, please take your final. Take your final. If you have any questions leading up to that, let me know. If you have any late labs, please turn them in. Please turn in your late labs. That would be great. But if not, good luck. Thanks for going on this journey through physical geology with me. And take your final.